Today I'm going to answer another question from a student by the name of Joseph Griscavage. And his question is, can you explain an isolation transformer, particularly how it pertains to testing with an oscilloscope? Let's start with a quick review about how transformers work, and you can skip this if you already know about it. A transformer is made with two or more coils of wire that are wound in close proximity to each other. So I have here the schematic symbol for a transformer, just two coils of wire next to each other. And the transformer is usually wound on an iron core made of either laminated plates of soft iron meaning that it does not retain magnetism. If you put a magnetic field around it or put it into a magnetic field, you take that magnetic field, it does not retain the magnetism. And so they use what's called silicon steel, or quote, soft iron, for the core. And that's represented by two straight lines. And let's put some alternating current on here and see what it does. So there's an alternating current source. It could be a generator, could be an oscillator, whatever we use to generate alternating current. And that means that the current's going to go back and forth in this side of the transformer. We call this side the primary because that's where it's being excited by the alternating current or whatever signal we are putting in. And over here is the secondary. Let's complete the circuit here with a resistor. So we have alternating current going back and forth in the primary. And as we know, whenever you have electric current in a wire, you have a magnetic field around that wire. So with alternating current, that field builds up. And as it builds up, it crosses over the secondary winding. And then it collapses. It reverses polarity, builds and collapses again, over and over again as the current reverses direction in the primary circuit. So we have a magnetic field moving across the secondary and then collapsing, reversing polarity, moving across the secondary and collapsing. And we know that when you have a magnetic field move across a wire, or you move a wire through a magnetic field, you get a current induced in that wire. And so we get a current that goes one way and then the other way, back and forth and back and forth. So if we excite this transformer with alternating current on the primary, we get alternating current on the secondary. Now, if these two coils are wound with the same number of turns of wire in each coil, that would be a 1-to-1 ratio, whatever voltage we put in, let's say 120 volts, is the same voltage we get out. But let's say we have a lot more turns on the primary than the secondary. So let's say we have 1,000 turns on the primary and 100 turns on the secondary. That would be a 10-to-1 ratio. We would have a step down in voltage. So the side with more turns of wire is going to have a higher voltage than the side with fewer turns. So here's 1,000 to 100, 10-to-1. We end up stepping down the voltage by a factor of 10. There we have what we would call a 12-volt transformer. We usually rate them by the number of volts on the secondary. If we reverse that, let's say we have 1,000 turns again on the primary. And it sounds like a pretty big number. Let's make that 100 turns on the primary and 1,000 turns on the secondary. Now we have a 1-to-10 ratio. And now we get a step up. So we put 120 in, we would get 1,200 volts out. You can actually reverse a transformer to make it a step up if it was a step down. It doesn't always work, but I've actually done that. I've taken 12-volt transformers and I've stepped up 12 volts to 120 volts, making a rather crude voltage inverter. So that's the step up and step down properties of a transformer. Now the main property we're interested in as an isolation transformer is the fact that there is no galvanic connection between the two circuits. Galvanic is just a big word meaning that there's no physical electrical connection. There's no wire in between them, so I cannot get any currents to flow. The only thing that moves from one side to the other is magnetic flux. We have this changing magnetic field, and that's what induces the energy. So no current can flow one way or the other in a standard transformer. So that's one of the properties that we exploit to make an isolation transformer. Now, an isolation transformer is also enhanced for other properties. For example, we want very good high voltage insulation. So we have insulation that's good for thousands of volts, to minimize any microcurrents that might flow through less high quality insulation. So all transformers, except for auto transformers, which I will mention later down the road, all transformers will isolate us electrically. We don't have a galvanic connection. Isolation transformer will also be optimized to give us good high voltage insulation to reduce leakage currents. And another thing we want to minimize is capacitance. If I draw a capacitor, what do we have? Two plates of metal separated by an insulator. And if I put a battery on here, and I'm going to put a switch here just to facilitate what I'm going to talk about. Let's assume that capacitor is completely discharged. So when I close this switch, current is going to flow into the capacitor, and it's going to pile on charge onto the side. In this case, we're using conventional current, so that's positive charge. And we always use conventional current in this class because that's the industry standard, and it just helps us visualize what's going on. Of course, what's really happening is electrons are going the opposite way, and electrons I'll represent with little negatives are piling on this side. But anyway, what happens, I'll talk about that this way for a second. As electrons pile on this side of the capacitor, the negative charge drives electrons off the other side. So we see electrons go in, we see an equal number of electrons come out. It's like cars going into a tunnel. We see 100 cars per minute going in, we see 100 cars per minute coming out. There must be a connection from one side to the other. But what if those 100 cars per minute are going inside and parking, and from a completely different part of the tunnel we have 100 cars per minute driving back out? Can we tell the difference? No, it still looks like there's a current of cars going through the tunnel. Well, here the electrons are actually not going through the capacitor, but it sure looks like they are, because as each electron goes in, another electron goes out. So we have a current that flows through the capacitor. Of course, it's very short-lived, because eventually we get enough charge that it pushes back on the capacitor enough that it can no longer push electrons in, and then that capacitor looks like exactly what it is. So we have a 10-volt battery over here, and current has flowed into the capacitor, but now it's fully charged. So it's pushing back just as hard as the battery's pushing in, and so no current flows, and the capacitor looks like exactly what it is, two conductors separated by an insulator. Well, what do we have here at the transformer? We have two conductors separated by an insulation. Looks like a capacitor to me. Can we get capacitive coupling from one side to the other? As current goes in, do we get a charge and it causes current to flow in the other side? You bet it does. So an engineering model of a transformer will put a capacitor here. That's not a real capacitor, it's just representing the natural capacitance that we have in the transformer. And that illustrates that we do have capacitive coupling from one side to the other. So when we make a isolation transformer, we want to minimize that capacitive coupling. And the way that is done is often, well, let's take a look at the construction of a typical transformer. Here is the laminated iron core. Looks like it has two little windows in it. And the transformer will usually be two coils wound on a plastic bobbin that goes in the middle here, and they'll just wind the primary and then the secondary right on top of it, or vice versa. So we want to get those coils in close proximity so we get good coupling. In an isolation transformer, it's going to be built more likely like this. Instead of having that two windows with the coils wrapped in the middle post, we're going to have one coil over here and the other coil over here. The laminated iron will conduct the magnetic field across, but we have the coils further apart from each other, so we don't have as much capacitance. Another popular way of making isolation transformers is with a ferrite toroid. Ferrite is a material made of powdered iron and clay, and it has good electromagnetic properties for making transformers. The laminated steel plates here are coated in lacquer so that they're insulated from each other, so we don't get currents flowing inside the core. And because this iron is powdered and the pieces are separated by ceramic material, we also don't get those eddy currents, but we do get a concentration of the magnetic fields, we wind one coil over here and the other coil over there. That gets them apart so we don't get a lot of capacitance. So it's common to have isolation transformers wound on ceramic toroids rather than frames like this, but you might find them made either way. And finally, if we go back to our schematic drawing of the transformer, we have our iron core. They will also build a Faraday cage around one of the coils, probably the secondary, and they do that pretty much by just wrapping it with foil, and then they will, let me just make a little room here for me to draw. They will put that metal foil represented here by that line, and that will be grounded. And that prevents electromagnetic radiation coming from one side to the other. All of the coupling, all of the energy goes across through moving magnetic fields. And if we get any high frequency currents going over here that tend to create electromagnetic radiation, that will be stopped by that foil shield, which we call a Faraday cage, that's wrapped around the secondary. So that's the construction of an isolation transformer. A transformer by its very nature isolates us galvanically, so there's no electrical connection from one side to the other. We have good insulation to reduce any kind of current leakage that might get through lesser insulation, so we don't have any microcurrents flowing through. We separate the coils so we have the minimum amount of capacitive coupling, and we put a Faraday cage around the secondary, most likely the secondary, to prevent any electromagnetic radiation from getting from one side to the other. So where do we use isolation transformers? One scenario is between two circuits where we might get a ground loop. So let's say we have circuit A over here and circuit B over here. Just off the top of my head, it seems like the most common place to find ground loops is in audio circuits, sometimes video circuits. In audio circuits, we hear that effect of the ground loop as hum, because the 60 hertz from the mains gets into the system in such a way that we can hear it. Or in video systems, sometimes we get horizontal bars. In the days of analog video, those bars would slowly creep up the screen. And so we have a signal going across. So there's our two wires with the signal, but these are also grounded. Let's ground this one. It doesn't have to be a true earth ground, so I'll just make it a common ground. And we'll connect that one over here. This can happen very commonly by having audio equipment, and we plug one into one wall socket and the other into another wall socket. So here's the ground of wall socket A, and here's the ground of wall socket B, and they're not in the same place. And there's two problems that can happen with this. One, we have power supplies in here that are plugged into the wall. And we get alternating currents going to the ground. And it's going to flow that way, and here's another alternating current, of course, is going back and forth and back and forth. Well, you can see there's a substantial amount of wire here, so we're going to get some voltage here, some alternating current there. So basically, this whole system here has a voltage that's going up and down and up and down and up and down compared to that one. And that can result in us hearing a 60 hertz or 50 hertz hum, depending on where you are in the world, on our speakers, or we can see those horizontal bars in our video. Another thing that can happen, which is probably why they call this a ground loop, is this acts as a loop of wire and can pick up electromagnetic radiation or fluctuating magnetic fields that are in the room you are in. And in the modern world where we're powered by alternating current, there's a lot of magnetic flux and low frequency electromagnetic radiation all around us, and this can pick that up and inject it into the system, and once again you would hear that 50 or 60 hertz hum in your speakers or see the horizontal bars. So what can we do to eliminate the ground loop? Well, one thing we could do is make sure everything's plugged into the same place. But if that's not feasible, or this might be inside in a single enclosure and we're just coupling between two circuits, and we have this problem if we ground them together, especially if it's not done properly. So what can we do? Well, typically if we have the signal going across, this is also going to be grounded. That's going to be the zero reference, and then our signal goes on the other wire. I'll represent that with just a pretty bad sine wave here. And because this is grounded and that's not, it's an unbalanced signal. Signal can get into this wire, and whatever gets in there electromagnetically or magnetically or whatever is going to simply be mixed with whatever signal we put in there. So how can we eliminate that? Get rid of this ground. Instead of having that a 0-volt reference, make this a balanced signal. So we have two wires, and the signal we send across is going to be balanced, meaning that instead of a 0-volt reference and our signal being on one wire, we have a signal on one wire. I'll represent with just some sine waves here, going up and down and up and down. That's what alternating current is. So the voltage here is going up and down and up and down, and we'll have a mirror image on this wire over here. So when this goes up in voltage, that goes down in voltage and vice versa. Now you might look at that and say, well, aren't they just going to cancel each other? Well, yes, if you just simply put them together, but we don't. At the other end, we'll have a differential amplifier that only looks for the difference in the signal. So this is going higher voltage and lower voltage. They're going different directions. They're going to be a different voltage. And as they come together, we get the same thing. So this is only going to see the differences. And any noise that gets in is going to be the same on both wires. So if I increase signal here, it's going to be identical. The differential amplifier will ignore whatever's identical and only amplify what's different. The other solution, which may be the more simple one, is simply use an isolation transformer, because that creates the differential signal. This could be grounded here, no problem. So I'll ground that. There's our primary of our transformer and our secondary, and we'll have that close to the circuit, and now the signal going over this way is a differential signal. How do we receive that? Well, we could use a differential amplifier, or we could use another isolation transformer in here, ground one side, and then we end up with a unbalanced signal again in the circuit where we need to go. So that's one use for isolation transformers. Another one's rather similar. Let's say we have two circuits we need to couple together. Just one thing that comes to mind, let's say we have a computer and we want to digitize some sound. So we have our wire that plugs in. This is going to be a wire that's got a wire with a braided shield around it, so two conductors. I'm just representing that with two straight wires. And let's say it's coming from a old-timey cassette deck. And we want to take these old-timey cassettes and digitize them. Well, we might find if we plug this into the speaker output of the cassette player that the signal has some DC bias or some other property that's incompatible with the input here. This is not designed to go in here. It's probably going to be too much energy, so I have to turn the volume way down, but still might get some distortion, which could be caused by DC bias, meaning that we have both alternating current, which is our signal, which is going to be alternating current that goes from 20 times per second up to 20,000 times per second. But it'd be really convenient if that signal was centered on 0 volts. So there's my 0 volts. And so let's say it goes up to plus 0.5 volts and down to minus 0.5 volts, which would be typical of a line level audio signal. That would be our maximum value there. But let's say this is not 0 volts. Let's say there's whatever the circuit is. If we try to connect these together, let's make that our ground. So I put my voltmeter here and I check here. I find out that it's not centered on 0 volts. I see that it's centered on, let's say, 3 volts. Which means this is going to be plus 3.5 volts, and this is going to be going down to plus 2.5 volts. And so it never even gets down to 0. 0 volts is somewhere down there, and this is definitely incompatible with the other side. Very simple solution to that is simply use a isolation transformer. You can get small audio level isolation transformers. They're just little things, and they have a 1-to-1 ratio, so signal in equals signal out. And we've isolated the DC because there's no direct connection across here. Direct current cannot go through a transformer because only thing that can go through is a moving magnetic field. And does DC create a moving magnetic field? No. Let's just look at that real quickly. We have our coil here. Let's put some DC on it. I'll put a switch here to facilitate that. I close the switch, current flows, I get a building magnetic field, and it stops. So there's my magnetic field not moving. To get a voltage in the secondary, or a current in the secondary, that magnetic field must be constantly moving. Well, it builds and it stops. I open the switch and then it collapses. So when I close the switch, I get a pulse of current going that way, then it stops. I open it, the magnetic field collapses, I get a pulse of current in the other direction and it stops. But the steady DC voltage will not go through. So the same thing happens here. That mismatch in voltages, the 3 volts doesn't get through. All that gets through is on the other side. Once I go through the transformer, I'm centered on 0 volts because that's according to this side. I'm measuring according to a 0 volt reference over here. I see the voltage going up and down by 1/2 volt up and 1/2 volt down, and that's working just like I expect. So that will block any DC from getting from one side to the other. So that's another use for an isolation transformer, is basically a DC block in this particular case. Now, another use for an isolation transformer is galvanic isolation from the mains. Once again, that's a $10 way of saying I don't have a direct connection for current to flow. It's all magnetic flux. So let's take a look at our power system. Here is our generator, which generates our electricity. And that's going to go to a transformer somewhere. This will be a very high voltage. We're going to step it down to something more reasonable that I can use. And that's going to go into my wall plug. Okay, and this is going to be grounded somewhere, most likely very close to the transformer. It could also be grounded in my breaker box in my building, but we'll just show it being grounded there. And we have short runs of wire over to our wall plugs. Now, when we measure our voltage, we measure according to where ground is. So we put our black lead here. That becomes 0 volts. Ground is not 0 volts because it's something magical. Ground is 0 volts because when we use the ground as part of our circuit, we measure our voltages from there, and that automatically makes ground 0 volts. So down this wire here, I should have 0 volts there. And this is a 120 volt transformer in the States here, so I would expect to have 120 volts AC here. So we call this wire with the 0 volts on it the neutral. And we call this one the hot wire because we expect no voltage here and our full voltage up there on the hot. Now, when we have a lot of current flowing through here, we will have a small voltage here, hopefully not too much. It depends on how much current's flowing and how long this wire is, and therefore how much resistance. But if there's no current flowing, that should be 0 volts, and that's my neutral. Okay, let's see how this can become a problem. Now I'm going to have a piece of equipment over here. I'll just draw a box for a circuit, and it's plugged in. I have 120 volts here and 0 volts there. So far, so good. And now I'm going to stand over here. And what's going to happen if I manage to touch that wire right there? Well, first of all, I'm just standing here. I'm floating. I'm not connected to ground. With no ground connection, I can touch it there, or I can touch it there. I can touch it anywhere. As long as I don't create a complete loop to ground, I'm safe. But we never assume that we're not grounded. We're going to assume that I'm standing barefoot on a wet concrete floor that has a good solid connection to ground, so I am grounded. Now, once again, touching the neutral wire should be safe. Unless there's a miswiring somewhere. I've seen them wired backwards, especially when amateurs get involved. Sometimes people wire their own houses. I've been there and they don't call an electrician. I've seen them wired backwards. Or if there's a lot of current flowing through there, I might get enough voltage to get a little bit of a shock, but it could be dangerous. I don't want to be touching that. But especially if I touch that side, now I have 120 volts between me and ground. Now, no big deal, except that ground is connected right there. So that means I have 120 volts going across me. If conditions are right, probably I'm going to be okay, but it's theoretically possible under the right conditions that I would have such a low resistance and such a good connection to ground that this could be deadly. So we always assume it's deadly because maybe as much as 9 times out of 10 you might be safe, but that 1 time out of 10 it's going to kill you. So we don't want that to happen. So what do? We will take that device and put it in a metal box. Represent that with some dashed lines. And I will leave it ungrounded for now. There I am, connected to ground, of course, because we always assume that I am. And what happens now if I touch that box? Well, it's not connected to anything, so I'm safe, right? What if I get a fault? What if something connects? I'll just show the 120 going directly to there somehow. Wire got frayed and stuck up. Something came loose. Some insulation broke down, who knows what. And I have a connection straight to that box. So now that is at 120 volts. And if I touch that, once again, I have the 120 volts going right through me, so not good. So what do we do? Well, of course, I'm leading up to this. We ground that box. Now, should I get that fault, I'm going to get current going through that metal chassis straight to ground. And that's going to have a very, very low resistance. So what that means is, even though I may get a high current, that low resistance means it can't build up enough voltage to be dangerous. Now, you've probably heard that it's not the voltage that kills, it's the current that kills. Yes, it is, but you're not getting current without voltage. The reason this makes things safe is if I do get a connection, this is a very, very low resistance, much lower than the impedance of this whole system over here. So low enough that even though I might get a lot of current, I get very little voltage. So that if I do touch that, I'm safe. So that's all I need to do is ground that, and no problem. Unless something goes wrong with the ground. Now I've got that full 120 volts across me again. So it's in the right direction, but if we have a double fault connection there and a loss of ground, I'm still in danger. So what can we do? What we can do is add an isolation transformer. Let me move this back a little to make some room here. So we come out of the wall. We'll assume that wall connection is right here. Here's our isolation transformer. In this case, it'll be just a 1-to-1 transformer. They often are. Now, isolation transformers might be tapped in a way that we can have multiple input voltages and multiple output voltages, but the classical isolation transformer is a 1-to-1, so 120 volts in, 120 volts out. Now I go to my equipment, put my metal box around it, and I still ground that metal box. Let's see what happens in these scenarios though. Here I am connected to ground. So under this condition, I touch the metal box, no problem. It's not activated, it's not energized. What happens if there is a fault? Let's say this somehow gets connected to that box again. Okay, so that box is grounded, I'm grounded, I have 120 volts to that. What's it going to do? Well, nothing, because this ground is in reference to this part of the circuit. There's no galvanic connection over to here. So I get this connection to the frame. It's energized to, let's call it 120 volts, but that 120 volts is referenced to the other side of the transformer. So it's irrelevant that that's connected to ground. So nothing special is going to happen. What's going to happen if I touch it? I'm touching ground, but that's referenced over here. There's no galvanic connection. So even though I am touching this side of the transformer, I am not getting a complete connection. Let's look at a battery that's just hanging in the air to get an idea of how this works. I'll make this into a 120 volt battery. And let's say I take my red lead of my voltmeter and touch it to the positive side of that battery. Am I going to see anything? Not if my black lead's just dangling in the air. What if I touch it to here? Same thing. What if I touch the black lead to here? Nothing. Not if the red lead's dangling. How about here? To get any kind of a reading, I have to connect my voltmeter across the entire battery. I'll put the black to the negative, red to the positive. It's going to tell me I have 120 volts. Remember, one voltage is meaningless unless you have another voltage to compare it to. Well, this is the voltage I can compare it to. Can I compare it to this voltage? No, there's no connection between them. So the only way I'm going to get a measurement is if I measure across there, and this voltage now is meaningful because it's compared to that voltage difference of 120 volts, and there it is. So you can try this. Take a 9-volt battery, touch your red lead to it. Nothing will happen. Touch it to either side, no reading. Take the black lead. You won't get a reading unless you put the black lead at one side and the red lead at the other. Take one side of that battery and connect it to ground. Find something that has a grounded chassis and test that battery. Touch the positive, touch the negative. Do you get any reading? No. Only if you have a connection from the positive to the negative. We have the same thing here. The only way I'm going to get any kind of a measurement is if I connect to that side and that side. That's what it's referenced to. This ground is irrelevant. So I've got the fault. I'm connected to ground. This is connected to ground, but the ground is irrelevant to the circuit because I have to somehow be connected that side of the transformer too. Only if I somehow get connected to the case and somehow get my other hand somewhere inside the chassis and connected there. Now, if that connects to the chassis, it just shorts the transformer out, and you're going to just blow the fuse on the transformer. So only if I manage to touch the case and get inside and touch the other side of that transformer will I get a shock. So the isolation transformer in this case adds another layer of protection against shock. Without the isolation transformer, all I need to do is touch the hot side, and I'm grounded. I get current through me because that's part of the circuit. With the isolation transformer, it's isolated. It's like a generator just hanging in the air. I have to touch both sides to get a circuit. So one more layer of protection by using an isolation transformer. Now, another place you might use an isolation transformer, this might be kind of rare, but I've used it this way, is as a protection against a direct connection to the mains when you are testing something and you don't know if it's going to be a short circuit or not. So here's my mains connection. There's my connection to the wall here. And I need to connect that to a piece of equipment to test it. So I'm going to plug it in, turn it on, and let's say, well, in my case, I was working at a place that built power supplies. We got the power supplies off the assembly line. We had to test them. Well, do we want to just plug them in and turn them on? Well, let's say there was a short circuit in there. Well, what's going to happen is this plug, let's say it's a 15 amp circuit. Actually, I might get as much as, who knows how many amps, 30, 40, 50. I might get a lot of current through there depending on what can be handled at the main breaker panel. Let's say I just get 100 amps momentarily because the fuse is going to blow or the circuit breaker is going to blow. But before that blows, I'm going to get a lot of current, and so I'm going to get spitzing and sparking and all sorts of stuff. I guess that breaker is going to be somewhere else, but anyway, I'm going to get sparks and smoke and welding and melting, and who knows what else I'll get. So what can I do to mitigate that? One thing to do would be to use a small enough isolation transformer that it cannot pass a lot of current. So let's say about a 30 volt amp isolation transformer. Now this basically is 30 watts. Rarely you might see them rated in watts, but most often they rate them in volt amps. And what's a watt? Voltage times current. So this is a 30 watt transformer. Well, they don't call it watts because transformers do not consume energy except for a little bit of waste in the core, because the little bit of currents flowing in there and the magnetic fields through there cause the core to get a little hot. You only have power if you have one of three things, either heat, mechanical motion, or electromagnetic radiation. And you get none of those from a transformer, just a little bit of warmth from the core. So it's improper to say that there's any watts being dissipated here, so they're often rated in volt amps instead of watts, which is the proper way to do it. You might see them rated in watts, but usually volt amps. So with a 30 volt amp transformer, I'm going to get perhaps about 2 amps max. I'm trying to remember off the top of my head some numbers. I think the output impedance is going to be like about 100 ohms. So basically this secondary looks like a AC voltage source with 150 ohms or such in series with it. Remember, all circuits have this model. Every circuit looks like a voltage source and a resistor or other impedance in series with it. So this whole transformer looks like a voltage source with a 150 ohm resistor in it if it's a 30 volt amp. I'm not 100% sure about this number. I might have it wrong, but it gives you the idea of what will happen. And of course, if I put a short circuit over here, if this is 120 volts, let's make this 120 ohms just so I don't have to do any math in my head. 120 volts, 120 ohms, that's going to give me a total of 1 amp of current. So even if this is a short circuit, I'm only going to get 1 amp. So I think I have that wrong. I think it's probably about half the resistance of what I said before. I think a 30 volt amp transformer can give you about 2 amps max, just off the top of my head. Probably rated at half an amp nominally, but might give you 2 amps max. And so I can do that momentarily without doing any damage. I don't get any smoke, sparks, or anything like that. And so I can use that isolation transformer as a protection against that direct connection to the mains. And actually, when we did this, when I was on that particular job, we used a variable isolation transformer. So the secondary coil had a wiper on it, so we could turn a knob and it would go from 0 volts all the way up to 120. And as I turned that up, we would have that go through a current meter to our device being tested. And if I saw that current going up, I knew there was a problem, crank it back down and start troubleshooting. So that was a variable. Let's run that to our, that's more like it. So as that voltage goes up, I watch the amp meter and see what happens. So I have a variable output, but be careful about this. This is actually not the most common way to find isolation transformers. And usually if you have a variable transformer, it's an auto transformer, which means it's made like this. It's a single coil of wire, and we definitely do have a galvanic connection across our circuit. And one thing I think is kind of unfortunate is that the catalogs I've looked at list auto transformers and isolation transformers in the same group. And auto transformers are definitely not isolation transformers. One brand name of that is called a Variac. And if I remember correctly, they actually label on there not an isolation transformer. So if you have a variable transformer and you think you want some isolation, make sure it's a variable isolation transformer and not a auto transformer, because there is no galvanic isolation if you do that. And now that brings us to the other part of the question. How would I use an isolation transformer when testing with an oscilloscope? Well, let's take a look at a test circuit. I'm going to put a battery here, and I'm just going to make some resistors, just a bunch of them, just to represent different parts of the circuit. Make that a little cleaner down here. And so I need to test this circuit. So let's say it's just a battery-powered circuit, no ground. If I want to take a voltmeter and check voltages, I can go look at that voltage, that voltage, that voltage, that voltage, no problem. Now let's do that with an oscilloscope. Okay, so I have my oscilloscope probe plugged in there. Let's try to draw a probe here. There's our little black lead with the alligator clip on it. Very crude drawing, but whatever, there's a little hook there. And I can measure my voltages with an oscilloscope and get a picture of any changes. So if this is alternating current, I can see what goes on. So I can take my leads. This is representing the alligator clip. There's my probe. No problem. However, let's say this is a power supply over here. There's my positive, there's my negative, and that negative is tied to ground. Now, it may be tied through the chassis. You may be able to connect or not connect that to ground. There may be a third connection where you can short that over to ground if you want that connected. But let's say that's the way we have to have it. Let's say we need to have that grounded. So this is ground. I'll just draw it here, but it's being grounded through the device. Now I'm going to take my oscilloscope and measure my voltages. No problem there. And something's not right. Well, because this, through the oscilloscope, goes to a true earth ground. So if I measure here, well, my alligator clip is connected to ground. That's above ground, no problem. But as soon as I put it here, I'm shorting this point to ground. Through my probe and back to here, I've shorted out that resistor. So I cannot measure that way with an oscilloscope. So what could I do? Well, what I could do is plug my oscilloscope into an isolation transformer. Just show that over here. You can buy these that have a plug that goes into the wall and either a pigtail you can plug into, or like this one right here, you have plugs right on the front. The problem with this is that this isolation transformer is going to have a grounded case. and that ground is connected to this ground, and so I'm defeating that. But there's a way to do it. You can make a cheater cord or get one of those little cheater plugs like that guy here and isolate that. And so you could isolate your oscilloscope from the mains and be able to do that. And I have heard of technicians that do this as a matter of daily practice, of having their oscilloscopes isolated through an isolation transformer. And I've heard engineers say that if they saw any of their technicians doing this, they would fire them on the spot. So you're defeating safety features to make this work, especially if you're using cheater cords. So you don't want to do that. I never recommend cheating. Yeah, I do it myself, but I'm very careful when I do. And I've made a few sparks when I wasn't careful. So no, Yeah, could get you fired, could get you worse. Not the right way to do it. Now, I've heard some say that it's appropriate to isolate the circuit that's being tested, but I think you're going to go through the same cheats there. So unless you can isolate it without cheating a ground, I would not do that. But there is a way to get around this without cheating, and that is just to use the oscilloscope in a way that a lot of people don't know it can be used. There's a couple of switches on the scope. Might be knobs, might be slider switches. One, we're assuming this is a dual trace scope, so there's our other probe. And I'm just going to take the ground leads off those just so they aren't even dangling there. They just pull right off. And I'm going to set this is my channels. So we have channel A, channel B, both, and add. Add. What good is that? Adds the two signals together. Well, it may not be very useful unless you go to the other switch, and that's your channel B, invert. I just wrote the word invert there. So there's A, B, both, add, and invert. You set that to invert, and now your oscilloscope becomes a differential voltmeter, just like your handheld voltmeter. One probe becomes my black probe, the other one becomes my red probe. So there's my black probe, there's my red probe. Well, you have to know which one's which. And I can now measure anywhere I want. And since that doesn't go to ground, it just shows me the difference in the two voltages, and it works just like a voltmeter. So if you need to use an oscilloscope and have a dual trace scope to probe around, and you have to look at the voltages across different parts of the components, use the scope properly. Do not isolate the scope. Use one probe as your black probe, the other one as your red probe. Now I prefer to say my red and black probes because you can put your red probe to a negative voltage. Yeah, so black probe to your lowest voltage, red probe to your highest voltage, probe around, and there you go. So that's the right way to use an oscilloscope to measure differential voltages, not isolating the scope with an isolation transformer. Now, another way you might use an isolation transformer with an oscilloscope would be to put your isolation transformer across the 2 points you're trying to measure. As long as this is a high enough impedance and you want to measure alternating current, you could do this. Get one that has a high impedance for high impedance microphones. And of course, that means you want to be doing audio circuits if you use that particular transformer, but it's a legitimate thing to do. And then I would hook up my probe. There's my probe hooked up there. My ground would go to there. Crude drawing, but you see what I'm doing. Now I'm using an isolation transformer to isolate my ground at the measuring point, and that's perfectly legitimate. So that's another way you could use an isolation transformer when using an oscilloscope. Not the improper way of isolating the scope from the mains, but simply isolating your circuit from the oscilloscope at the low voltage level. If you found this video useful and informative, please give me a thumbs up down below. It really helps the channel. And subscribe, because that not only informs you when I put new videos up, but it really helps the channel also. And a big thank you to my patrons at Patreon. I could not make these videos without your support. If you want to help me put these videos online and keep real vocational education free at vocatomy.net, you can go to patreon.com/join/vocatomy and pledge your support. And again, a big thank you to my patrons who make this possible, and a big thank you to everyone for watching.